Let's look at another scale ratio problem, but this one's a little bit different. This is one of those things that you might see in a documentary where they talk about the Earth being really, really old and human written history's not that old. And so the first question says, suppose the entire history is represented by a 10-meter long timeline. What is the distance that represents 1 billion years? So the entire history is 10 billion. So I would say 4.5 billion. That's 10 meters. And the follow-up question is, well, what is 1 billion meters? Or 1 billion years? It's not 1 billion meters. It's going to be less than 10 meters. And so all we're going to have to do, if we don't find x meters, notice that my billions of years and my meters line up. They're in the same place. And we're going to solve that proportion by going ahead and cross multiply and divide. So we get 4.5x equals 10, and so x equals 10 divided by 4.5. Now, that's part A. Part B says, how far from the end of the timeline does human written history begin? Now, human written history is not a billion years. It's only 10,000 years. Now, my problem is I can't just go ahead and cross multiply and solve this one as it sits, because this one is written in years and this one is written in billions of years. So we're going to make them both into years. So instead of saying 4.5 billion years, we're going to say 4,500. That'd be 4.5 million, but I want 4.5 billion. And then we can cross multiply and divide. Okay. Talking about mortality rate, suppose that many people died and the population of a country is this much. They want to know what is the mortality rate in deaths per 100,000. So the way we do that is we do the total population. We do the group that we're looking at, which in this case, the deaths. And whatever we get, instead of just saying that ratio, we want it per 100,000 people. So we're going to multiply those together. And so deaths is going to be 586,250 divided by 264 million. Again, pay attention that we're writing in the same units. 264 million means I'm going to go ahead and write 1, 2, 3, 1, 2, 3. So I've got 264 million written out. And then I'm going to multiply it by 100,000. And when we type that in our calculator, we end up getting the answer we're looking for. Your car gets 27 miles per gallon, 27 miles per gallon, per 1 gallon. How much does it cost to drive 360 miles when gas costs 340 per gallon? Okay, so the first question is, how many gallons would it cost to go 360 miles? How many gallons? So I'm just putting a question mark there. To go 360 miles. Well, this is just going to be a straight proportion. I can go ahead and cross multiply and divide. And when I do that, what I'm going to end up getting is 360 divided by 27 gallons. So whatever that ends up being, when I cross multiply and divide, I get how many gallons. But the question didn't say how many gallons is it going to take. It says how much it's going to cost. I also know that the cost per gallon is 340. So if it costs me 1 gallon, it's going to be 340. If it costs me 2 gallons, it's going to be 680 and so forth. So I know I need to multiply by 340 in order to get my answer. And when I type that in, I will get an answer. I want to make sure I use the right number of decimal places because we're talking about money. Consider the following exam question. So this is one where somebody has already solved it. And they said they went into a candy store that sells chocolate for $7.01 per pound. And they want to buy just a piece of it. Okay, they don't want to buy $7 worth of chocolate. And so they look at how much they have, and they've only got 0.17 pounds. And so their math is that it'll only cost them 2.4 cents before tax. And they think, oh, I'm just going to give them 2 cents. Now the question is, Is that the right answer? Well, no, that's wrong. The follow-up is, why is it wrong? Or how would you do that the right way? Okay, so they did something wrong because 2 cents for chocolate is too cheap when they're selling it for $7 a pound. We need to make sure that we're selling it for the appropriate representation. So I'm going to do this with a proportion. I'm going to say $7.01 per 1 pound. And this time we have how many pounds? 0.17 pounds. Notice I put the pounds with the pounds. They're both on the bottom. And what I want to know is what is my dollars right here, okay? And we can cross multiply and divide. So if you look at what they did, they actually took 701 and they divided 0.7 when we should have multiplied. Let's look at an electricity problem. We have the company charges 15 cents per kilowatt hour of electricity. So the first part we have is, let's say we have a light bulb, and the light bulb is a 60-watt light bulb, and that means it uses 60 watts each hour, and then we use it for 13 hours each day. So I'm going to go ahead and figure out how much electricity it uses in a day. So I do 60 watts times 13 hours, and I end up with 780 watt hours. Okay. They told me that they're going to charge me 15 cents per kilowatt hour. So if I multiply that by 0.15% per kilowatt hour, you'll notice that it actually doesn't cancel out because we have watt hours on the top and kilowatt hours on the bottom. So we need to kind of do some math here, okay? So what's the difference? Well, the difference is that a kilowatt is 1,000 watt hours, okay? So in other words, we can also say that 780 kilowatt hours, or watt hours, is equal to 0.780 kilowatt hours. And then we can multiply that by that 50 cents. And what we're going to get is that it costs us, a few cents a day. Let's say 11 or 12 cents a day. You'll notice that if we wanted to save money, we could replace our 60-watt light bulb with an LED bulb that is just as bright, but it only uses 10 watts. Okay, so how much would we save? Well, if it only uses 10 watts and we're using 60 watts, we're going to save 50 out of 60. We're going to save 5/6 of our costs. So in order to calculate it, we're going to go ahead and multiply our cost per day times 365 days in a year. And that would give us our total cost for the year, but we're actually going to save most of that because we're going to switch to a more efficient light bulb. In a certain country, the life expectancy for women in 1900 was 47 years, and then it turned into 80 years. So it went from 47 to 80 years. So it went up. How much did it go up? So it went up 33 years. I just subtracted those, right? So what percent increase happened? Well, our percent increase that happened, what we need to do is we need to take our new minus our old, 80 minus 47, and divide by our old, or our original amount. And if we do that, we end up with the 33, the amount it went up, divided by 47. Okay, so it's, sorry, I'm going to use my calculator here. That's going to give me my percent increase. If I use my calculator, I get 33 divided by 47. And so that's 0.70 or 70%. Okay. Now here's the catch. If it says it's going to keep increasing for another 100 years. If it keeps increasing at the same rate, does that mean it's going up the same number of years? Does it go up 33? Well, no, because it's not going up by 33 years each time. It's going up at the rate of 70%. And so we need to figure out what is 70% of that 80. So we can do that pretty quickly by doing 80 times 0.70. And so that's 56 years. So does that mean that the life expectancy will be 56 years? No, that means we add 56 years, and so that we end up with 136 years. Suppose that a certain basketball game, the athlete earned $23,500,000 to play 80 games, and they only take 48 minutes to play a basketball game, assuming they don't go to overtime. How much did the athlete earn per game? So first, we'd say, well, this is easy math. We just say they took the 23,500,000 and divided by 80, because that's how much money they made per game. However, the athlete might say, whoa, it's not quite that simple, because I played every minute of those games. And so we might need to say, okay, so if that's how much they made per game, then we take that and we're going to multiply that by, or divide that by 48, because that's how much they made per minute. All right. But some athletes don't even play the whole game. They only play 2/3 of the game. So what we're going to do is we're going to say, well, I don't need to divide it by 48 minutes. Instead, I'm going to take that amount and I'm going to divide it by 2/3 of a game. So 2/3 of 48 is 32. So they only played 32 minutes. Well, then we're going to divide that, and that will give us that. Now, the last part is that the athlete will say, no. You can't just say for the minutes I was there, because I worked for every game. And let's say that on average, they practiced for 33 hours and played every minute. What would their hourly salary be? Okay, so we're going to work this out here. So how many total hours did they work? Well, for each game, let's factor this down to hourly salary. So they started with this much money for the year, but that's for 80 games. Okay, but each game cost them 33.8 hours. Okay, why 33.8? Because of 33 hours for every game in practice, plus the 48 minutes, or 48 out of 60 for the time they played in the game. Let's take a look at the metrics that we can use in different situations. It's important that we know our metric units, okay? So a few of the ones right off the top of my head are millimeter and centimeter. You sometimes see decimeter, but we're not going to use that one too much. We're going to say meter. You might even see kilometer. And those are big metric distances, okay? But I want you to know that there's the other ones, that we could have all the same prefixes with weights. And you should have a roundabout guess about how big each one of those is. For example, a paperclip is probably going to be measured in millimeters. It's really small. And a width of a dime, probably millimeters. You could maybe say centimeters. A dime might be a centimeter wide. I don't know. If we're talking about the width or the thickness, then thickness should be definitely millimeters, right? A tall floor lamp might be measured in meters. It could be 2 meters tall. The width of a room would be meters, usually. A road race, so if you're racing on the road, you would expect it's probably with cars or bikes, so we're going to say kilometers. The wingspan of a butterfly is probably in centimeters, probably fair enough. But you might even say an eagle is in centimeters or in meters. I think eagles can get pretty big, so I'm going to say maybe in some meters. Shoe size, a meter would be too big. Everybody has shoes that are less than a meter big, so we're going to say a little bit smaller, centimeters. The width of a window, again, a meter is probably too big to measure most windows, but there are some windows that it's not too big, so depending on the situation. Now, I want to stop for a second and focus on this last one, because when we start talking about different dimensions, we talk about floor space of a tent. You might say floor space of a tent, it could be 3 meters by 2 meters, and so you could say it's meters. But the truth is, it should be meters squared, because when we're talking about area, we want squared dimensions. If we're talking about volume, we want cube dimensions. So I want you to watch out for that. I don't want you to get it wrong just because you picked the right, but you weren't paying attention to the units and the dimensions. House, 21 meters by 9 meters. Okay, so we've got a house and it's a rectangle. And it's 21 meters by 9 meters. And I can find the area of that house. I'd multiply those two together, and I get 189 meters. Again, we just want to remember that that's the second dimension, so 189 meters squared. Now, the question is actually saying, listen, we have this house, but we also have a walkway around the whole house. And so that walkway around the whole house kind of gives us a bigger rectangle. Can you kind of see how, if we imagined that the whole house had like a big rectangle, if it continued the walkway underneath the house, like the concrete, then we could have a bigger rectangle. So the question is, how big is that bigger rectangle right now? So if the walkway is only 1.2 wide in this range, but we notice it's 1.2 wide on both sides, 1.2 plus 1.2, that's 2.4. So it's 2.4 meters that is adding to each of our dimensions. So our rectangle is going to be 21 plus 2.4. So that's 23.4 meters. And 9 plus 2.4, so that's 11.4 meters. And so our big green rectangle, if we were to fill in the whole thing, would be those multiplied together. So I'm going to get out a calculator because I don't know that off the top of my head. So I'm going to say 11.4 times 23.4. And so the big one I got was 266.76. And it's going to be meters squared because we're talking about area. So what is the question? The question is find the area of the region covered by the house and the walkway. Well, guess what? That is what we just found. But let's say we don't want to include all the part that's both green and red. Let's say we want to take this part out. Well, how are we going to find that? So for part B, all we're going to do is we're going to take that 266.76 and we're going to subtract the 189 that the house is covering. And that would give us our answer for B. It's still going to be in meters squared,